All right. Well, welcome everybody. It is 2 o'clock. My name is Paul Abernathy, and welcome to our mini webinar series where we're going to talk about supply side bonding jumpers and load side equipment bonding jumpers. And not only talking about sizing and the concepts of them, but as a bonus, we're going to originally start out this webinar by giving you foundations on when we would do supply side bonding and talk about the services and things like that as the upfront portion to why we would have something like supply side bonding and all. And we'll move through that portion pretty quickly. So as we move through that, then we'll slowly move into what today's topic is. And today's topic will actually be supply side bonding jumper sizing and application and then load side. But as I said, kind of an intro before the recording started, I want to make sure that you have a fundamental foundation. Again, most people know that, again, grounding and bonding excites me. It's always my favorite topic, always. I think our grounding and bonding course, which is today's presentation, comes out of that, is probably the most detailed when it comes to grounding and bonding. There are other books available. There's other things that are, but this is a really detailed course on grounding and bonding. So we're gonna pull a piece of that out today and use it in the presentation. All right, so I'm going to go on and start sharing that portion of that presentation.
Hey, Paul.
Yes, sir.
Are you recording this one?
Yes, I am.
All right. Did you already hit it?
I already did.
You're the man.
All right, so we're going to be covering basically this whole concept talks about bonding. Now, we do understand that when we're doing load side bonding and bonding jumpers, that we're doing a bonding component, but we also, at that point, will be doing things like equipment grounding conductors, which serves two functions. Not only the connection for voltage potential to earth in order to keep everything at a certain potential. Usually the shocks and things that we experience come because of voltage potentials. That's why we call voltage gradients. The difference of potential creates that difference of potential, which creates the shock because of the difference of potential. And because of that difference of potential creates current. Okay, so it's not the difference of current potential, it's the difference of voltage potential. So when we run equipment grounding conductors, when we see this on the load side example today, and we're going to use, for example, the same tables we would use for sizing equipment grounding conductors, we're doing double duty here. We're doing bonding and we're doing grounding. Okay, now, the stuff that we're going to talk about first today is purely bonding. It has absolutely zero to do with clearing overcurrent protector devices because that takes place on the load side. Now, is there a chance that we will clear something on the line side if we do all our bonding correctly on the line side for supply side? Is there a chance? There may be a chance on the primary side of the transformer that basically the fuses are much smaller, that we could clear something, okay? But that's something electricians can't bank on. That is not our thing. We don't control that. All we do is follow the code. And so we follow the code because you'll find that if you follow the code and the minimum requirements of this code, we're about as safe as we're gonna get with an electrical installation, okay? So that's why we're gonna cover the principles up front when it comes to some of the aspects. Now, this comes straight out of our program in our grounding and bonding, which was written, the original author was Phil Simmons. And if you've got the document, you'll notice that I am one of the authors as well, and multiple chapters in that book. And working with Phil so many years, who is without a doubt one of the leading experts when it comes to grounding and bonding, without a doubt. And I like to tease him that says anybody that's been around as long enough to know Benjamin Franklin certainly has to know a lot about grounding and bonding, because Phil has been around a long time. And he's also a sweetheart of a guy. If you ever get to know him, if you ever go to an IAI meeting or something, he is just a sweetheart of a guy. And I was very blessed to be able to author with him. So after we study this today, I mean, again, our presentation today is going to be primarily focused on supply side and load side bonding jumpers. But I felt it's important that I always like to give people more value for their money. And so I said, why don't we put in there the whole principles of why we're doing supply side bonding, which is part of the service bonding, why we do it. So I wanted to incorporate that into it because I felt that I could cover that in 2 hours. So we'll see if we can do that. That's a lot to bite off, trust me, but we'll give it a shot. So we're going to summarize the general requirements of bonding. We're going to explain the bonding requirements for services so that we kind of understand why we're doing supply side bonding anyway. We're going to cover the requirements for bonding other enclosures that are not service related, that'd be load side. And again, we're going to be slowing down primarily in our supply side and load side area, but we're going to cover all the areas and try to give you a more rounded picture, but then we will slow down our approach when we get to today's topic. We're going to talk about the bonding requirements about loosely joined metal raceways, impaired knockouts, and all those things. We'll just touch on bonding and hazardous location very lightly, and then we'll summarize the material for these bonding jumpers, and we'll talk about sizing and finish up maybe with some lightning protection applications, but maybe even not talk about that in this episode. But I wanted to throw you a little bit more than what we normally would cover. All right, so let's start out. If you have your code book, and again, I'm working out the 2020 edition of the NEC. I don't notice a lot of changes. We'll say it where it is if you're in a 2017. Grounding and bonding being what it is, the principles behind grounding and bonding should be the same. Sometimes we change terminology, sometimes we change connection schemes, but in general, the concepts remain the same from the 2017 to a 2020. Now, bonding is required where necessary to ensure electrical continuity and must have the capacity to conduct safely any fault current likely to be imposed on it. This is so important when we're selecting raceways, connection points, metal boxes, tying things together. As you see in this illustration, from this 4-inch square box to this 4-inch square box, they are physically connected together. They are bonded together by the concept of this metal nipple to this metal box through these lock nuts in contact with this actual metal box. So this is the basic principles, okay, of bonding something to something. So box to box through a metal connective component between the two, okay? In fact, if I bonded this box on the left and I take a wire here, let's say an equipment ground to this box here on the left, that by virtue of these connections, it bonds to this box on the right, okay? Just basic principles. This is an exaggerated picture of basic principles where somebody said, well, I need all these raceways to be bonded together. So let's just run a bonding jumper between all these raceways. Chances are these are not service. So chances are they're already bonded together through their connections here at the enclosure. But somebody that was extremely overzealous and had a lot of extra money on the project to spend simply decided to do all this, and that's okay. Not necessary, but okay. All right, so the term bonded or bonding, now think about bonded. Bonded is the past tense. When you take an action and you do it, it's considered bonded. The action that we as electricians take in the process of doing this, the different connections, the selections of terminals, that's called bonding, okay? And once it's done, we're bonded, okay? So that's why they're synonymous in the definition of Article 100. But what does it mean? It means to connect to establish electrical continuity and conductivity. So boxes to boxes, equipment grounds to boxes, to switches, all this type of thing. When we're bonding all this together, we're establishing electrical continuity and mutual conductivity between all those contact points, okay? Bonding is performed in many ways. There's many people that used Article 250 to create a career, right? There's people that this is all they do, and they specialize in grounding and bonding, because if anywhere in an electrical system, you're going to have an accident take place, usually when you run circuits, the circuits just run. Everything continues to run. And power wants to run, loosely we'll say it that way, on the conductive medium, which is your insulated conductors and what have you. When somebody does grounding and bonding wrong or makes a connection to a grounded conductor, which a grounded conductor carries current, then you create a headache's worth of problems through the system, because electricity takes all available paths, not just the path of least resistance. It's going to take all paths. And that means it's going to put current on metal parts that are not intended to carry current, except for in a fault condition, which is for a brief amount of time. Okay, so if there's anything in an electrical system that electricians should be very well versed on, is grounding and bonding. Why? Because when you walk away from it, the system's still going to be working. but it might still be unsafe. It still works. And you walk away thinking, give me my money. Here's my green tag. And I'm walking away. But reality, it's just a ticking time bomb that somebody could come in contact with and could create a hazard. So that's why I'm so passionate about grounding and bonding, okay? The requirements include most all metal parts within Article 250 have to be bonded together, okay? There is some exceptions like metal elbows that are down lower than 18 inches that have service conductors in them. There's no way you're gonna make a connection to a metal elbow. And why would you have that? Because a lot of times if you have PVC, and you pull it and you pull larger conductors through an elbow, it can burn the inside of the elbow out, friction burn, and it can cause damage to the elbow. So they might use an elbow isolated metal elbow in that pull. That way it doesn't burn out the elbow. But then of course that is a metal part with conductors in it and which should be bonded by code. However, there's an allowance when it's lower than 18 inches below the earth that you don't have to bond that elbow. It's not in contact with anybody to touch it scenario. So there is different situations that we have to be aware of as electricians, okay? Now, let's talk about 250.92A, bonding of services, okay? So bonding of services, it says normally non-current carrying metal parts of following equipment must be bonded together. So if you got your code book, we're looking at 250.92A, and it says, number one says all service raceways, cable trays, cable bus framework, auxiliary gutters, and service cable armor or sheathing, except that's permitted in 250.80, which again gave you an example of what I was talking about, that with the elbows and whatnot underground, that type of scenario. It says all enclosures that contain service conductors, including meter fittings, boxes, or the like, interposed on the service raceway. So if you think about it, a meter is something that's imposed in the service conductor's raceway. Okay, you come from a weatherhead, if it's overhead, you're coming down the riser and you go into the top of a meter can. Then you come out the bottom of the meter can, and of course in the 2020 code, you're going to hit an exterior service disconnect. But in the old days, or in the 2017 code, we now come out of that, we turn maybe in an LB, and we go into the back of a main panel, right? That meter was interposed in the service raceway. So of course that meter enclosure has to be bonded, okay? So this is kind of an example of an overall scheme picture of service bonding applications. So this would be an overhead. Here you see 3 conductors coming down, coming into the weatherhead, coming down the riser. All right, so this raceway here is bonded by this hub to this meter enclosure. This meter enclosure is physically connected to the neutral conductor, okay, which is permitted to be done. This raceway here is bonded into a hub that is connected to this metal wireway, okay? So that's bonding this portion. You only have to do this at one end, so it's done at this end. And then, of course, this metal enclosure is bonded to the neutral through this lug system. And then, of course, then you've got these nipples, which supply these services, and you only have to bond one side of the nipple. You don't have to bond both sides, okay? In this case, it's bonded on this side where the service disconnect is. And here's your neutral, which is here's your main bonding jumper connecting to this enclosure. And then here's the connection from the grounded conductor terminal point. And this right here is a bonding jumper. And in this case, it would be a supply side bonding jumper. And it connects to this bushing, which is going to bond this side of the nipple, this whole nipple from this side, okay? So all of this is bonded together to create this service bonding of all of the service equipment that's covered in 250.92A, okay? So it's all pretty much tied together. Now, methods of bonding at the service. Bonding jumpers meeting the requirements of this article are required to be used around impaired connections, such as reducing washers or oversized. And when we say reducing, usually that's a fancy term for undersized. Okay, so reducing washers or oversized washers if you cut too big. Concentric or eccentric knockouts. So, concentric is where they all equally come out. Eccentric is the ones where it looks like the half moons. So you have a bigger one and it's smaller kind of little pieces that come out from it. All of those are considered impairments. In no case can you have that on the service side with service conductors coming in. you have to use, on any of those situations, you have to have a bonding jumper. There is no exception. If you're going to leave those impairments in place, if you're going to do reducing washers, all of that, then you're going to have a bonding jumper. Okay. And we'll look at some other allowances, but that is a given. Okay. Now, standard lock nuts or standard bushings must not be the only means for bonding requirements by this section, but are permitted to be installed to make a mechanical connection of a raceway. So, in other words, standard lock nuts come in with a raceway, come into an enclosure through a concentric or eccentric or whatnot. A standard lock nut is never going to be adequate to make the bond connection between the raceway and the enclosure. Okay. And when I say standard's never going to be allowed, standard lock nuts are never going to be allowed, even if you didn't have these impairments. You cannot use standard lock nuts, period. Okay. We'll have to do something else, but we can't use it. Now, if you want to do it for mechanical purposes, and I'll show you an example of where you would do this if we're doing what's called a bonding wedge, then you would want to have a standard lock nut as a mechanical, for strength, but not to be the actual metal to metal bonding component. It's not what you're going to use now. Okay. So in this case here, at a service equipment, when used with a metal conduit or EMT, which is a tubing, bond around all impaired connections, such as the ones we just talked about, reducing washers, oversized, concentric, eccentric, what have you. These, for example, here are concentric. You can barely see pieces of them here. And so in this case, somebody goofed up, and here they had to put this ring on it. Okay. So at the service equipment, when used metal conduit or EMT, this will be rigid, intermediate, things like that, around in impaired connections. And in this case, they're using it was called a reducing, but it's actually an oversized because they probably knocked out too many. But another thing to remember is, even if you have a situation where you have paint, you have to remove the paint to make that connection. And we'll see that later when we have some other options to be able to make this connection. But one thing I want you to take away from this, and a lot of people miss, is if there's an impairment at all, concentric, eccentric, even they get to them and it just some type of impairment that's going to impede this connection, you're going to need a bonding jumper. Okay. At least for the service side. So we're going to size those later, but it's important to understand why we need them first. Okay. So this here would be a bonding jumper. And if it's for the supply side, it means on the line side of your service disconnect, these are supply side bonding jumpers. Okay. Now, bonding of these enclosures is to be ensured by one of the following. Okay. So we're going to make these connections here. Number one, bonding equipment to the grounded service conductor in a manner provided by 250.8. So what we're saying is, okay, so I have to make these connections and I have to make this to these raceways. I need to make sure that all terminals are done in compliance with 250.8. Now, 250.8 gives me a list, and it tells me about the different lugs, listed lugs, different connections, and it's a laundry list of ways to make these connections, okay, when you're doing bonding, okay? And we'll look at an example, but here was, so we have to make those connections. And if you look at it, so you have your code book, and if you go to 250.92, and you're looking at B1, it says bonding equipment to the grounded service conductor, okay? To the grounded service conductor. So even from my lug on my bonding bushing, that supply side bonding jumper is going to go up from that lug up to my grounded terminal bus, because that's the bus that's going to make the connection to my grounded service conductor. It's just telling me that I need to use the methods in 250.8. And of course, all panels probably have the lugs already, that have a terminal bus with the lugs. So that's pretty much taken care of. You just need to know that it's a situation. In this case right here, this is an example of where the neutral conductor is, all the connections are being made back to the neutral by proxy of different types of bonding methods. So here's your CT, for example, and here's your grounded neutral conductor right here in this CT, right? So this connection right here is making this connection over to the case. So that bonds it. These raceways, remember, have to have something a little bit better. You can't just use lock nuts. In this case, we'll assume that it's coming in here and there's an impairment. So they're putting in right here, bonding over to this closure, which is connected through here. So this connects to this, bonding this. This raceway connects here to this, that bonds this raceway point. Same with this one here. And of course, now this is a supplemental, which isn't, this is actually an example of the way it's connected. Could be two ways. It could be considered an auxiliary gutter or a wireway. Auxiliary gutters are supplemental space to afford the wiring to get from point A to point B. An auxiliary gutter would be typically in this picture, if I went from the CT here through a raceway to a separate wireway, then I would consider that a wireway. The way this is connected, I could argue this is an auxiliary gutter. It's providing additional wiring space. Why is that important? Well, if you probably know that there's different rules for auxiliary gutters than there are for wireways. So we have to differentiate what we're dealing with, but we're getting additional wiring space. Okay. All right. So anyway, so this here is bonded here. So it's bonded back to this CT that's bonded to the neutral. And then down here, we've got our nipples. And so this is the next component. So we already know this enclosure right here is connected, okay, to the neutral because it carries on right here. And then you see here, this is our main bonding jumper right here. See, it doesn't always have to be in the same bus. So here's a wire type main bonding jumper, which over here then connects to the enclosure. So here's the grounding conductor. So this nipple is getting bonded on this side from a bonding bushing. And here is, and that is also still a supply side bonding jumper. So as we go through the day, we'll be sizing all of these because all of these are supply side bonding jumpers. Okay. Now, if I had a raceway coming out down here, going out, then that would be a load side bonding jumper sizing. But again, we're talking about all supply side right here. All right. So that's just one example of it. So in a remote metering situation, this is very common. As you can see here, we're using, this is where it's coming in from an overhead, and then it's going to come into a meter. And let's say it's going to continue overhead onto the dwelling. Okay. They're not going underground. They're going overhead. Okay. You can, at this point, this is just a meter. It's not the service disconnect, it's simply a meter. You can have an electrode installed here if you want. It's considered auxiliary. It's not required. This would be done over the service disconnect, but it doesn't hurt anything. In this case, they installed one. Verify the neutral terminal is bonded to the enclosure. Most all residential style meter sockets, the neutral connection is going to be made to the actual meter enclosure. So that's going to be a given in the equipment. If you ever question that, and again, sometimes you can question it. Why? Because you want to make sure that somebody doesn't give you what's called a tenant side meter. Because in a tenant side meter, then it would not be connected to it because that would be a load side connection and that would be a violation of 250.24A5. So you can't have a case to neutral connection downstream. So I tell people all the time, and also in those, you typically wouldn't have a hub in the top, but I always tell people it's always never fails to take a continuity tester and test from the metal enclosure to the neutral bus. And if it doesn't ring out, then you can dig a little more and usually you'll see that that's a tenant side meter. Okay. It should ring out if it's connected from the grounded neutral to the actual meter enclosure. It should all ring out. Okay. Just kind of one of those little steps that you do just to make sure, that type of thing. Okay. Now, it also says a connection to the grounding electrode may be required by your utility. There are many utilities out there, believe it or not, who don't see this as an auxiliary, as an extra. You can do it if you want. They want it there. Okay, that's fine. That's why it's in the code. That's why the code permits an auxiliary. They can do that as well. But if we follow the rules in the code, the grounding electrical conductor can actually, to grounding electrodes can be anywhere on the line side of the system. So it doesn't have to be just in the service. There's many places it can do, but typically that's not where we do it. But here, if they want one, okay, that's what you want. I'll give you one. It doesn't hurt anything. In fact, to be honest with you, if I make multiple connections on the line side to electrodes, it doesn't really hurt. Utility does it all the time. It just gives you more connections to the earth. It's not going to hurt anything. Okay. But it's not necessary for this case right here, but you might get a power company that requires this connection. Okay. And, My advice when arguing with the power company on something like this, it doesn't really matter, is say whatever you want, dude. Because the last thing I want them to say, you know what, do you want power or not? So, I'm like, yeah, I want power. So, okay, whatever you want. All right, so this is another example of a remote metering setup. There's probably more indicative of a commercial application. And as you can see right here, coming in and then going out is a remote metering setup with CTs on a remote meter, part of the CT system. Here, again, not brain surgery. The grounded neutral conductor is making connection over to the case. That is bonding the metal case. That is already taking place. And this connection is just like the others. They might want this connection to be made right here. Of course, code allows us, again, to make the connection to the grounded electrode to the grounded conductor anywhere on the line side of the system, or all the way up to including the service disconnect. So if this is what they want, whatever, I'll give them what they want. A lot of people don't allow this because they feel that you can't get to it later. So in some places, some jurisdictions will say, I don't want it in the meter, which is kind of ironic because in some places they say, I want it in the meter. And then you go to other places in the country and they say, don't put that grounding electroconductor in the meter. Don't put it in the CT because we're going to seal that thing up and it's not accessible anymore. Well, it doesn't have to be readily accessible. It only has to be accessible. And again, it's accessible to anybody that needs to get to it. Okay. But it just depends on the jurisdiction you're in. I'm not going to argue with them. If they don't want it here, I'm going to put it at my service disconnect and everybody's going to be happy. But it could be here. Code allows it to be here. Okay. The point of these slides is to show you that grounded neutral conductor is going to be utilized to bond the metal enclosures on the supply side in many cases. Okay. Now, if this was a direct screw that went into it, then I wouldn't have to worry about a bonding jumper. And I wouldn't have to worry about sizing it. It came with the equipment. But in most all of my examples, I'm going to force you to have to size something because it's a little funner to have to do that.
Hey, Paul.
Yes, sir.
So when you do, if you can go back to that slide.
I'm there. Is it on?
All right. So say that you bond the neutral here and you bond it at the disco, the main.
At the service disconnect?
Yeah.
Yeah. So,
okay.
So understand that this isn't considered a main bonding jumper. This is just a supply side bonding jumper. The connection that you're going to make at your service equipment from the grounded conductor to the enclosure, that's called a main bonding jumper. Okay. And remember, the function for that is to make sure that you clear overcurrent devices downstream in case any of the metal parts were to get energized. At this point, all you're trying to do is bond everything so everything's at the same voltage potential, right? So we don't have differences of potential so that you could run a risk of getting shocked, because that's how you get shocked, is at differences of voltage potential, okay? Current's not generated until you have those difference of potentials. So at the beginning, the real focus, if you look at it, it's voltage potential. That's why if you look at equipotential bonding, that's why you look at agricultural buildings, it ain't about the current, it's about the voltage potential. When you have voltage potential, then you're going to increase your current, okay? Unfortunately, it's the current that kills, not the voltage potential. But if there's a great enough voltage potential, then you're going to have a greater element of current. And so they are inversely proportional. Does that answer your question, hopefully?
Yeah, thank you.
Yep. All right. So we move on to next connections. So at 250.92b, bonding equipment to the grounded service. Number 2, connections utilizing threaded couplings or threaded hubs on enclosures if made up wrench tight. So again, what we're doing now is we're talking about, again, bonding. So another way to do this, if I wasn't, I'm bonding all these enclosures, I'm allowed to use hubs, which is there's a hub on top of this. And then this is like what's called a Myers hub here, okay? And they have to be listed for grounding and bonding applications. Don't take for granted that all Myers hubs are listed for grounding connections. Do a little research, but again, manufacturers have gotten pretty savvy with this. They will actually tell you on the literature for the equipment because they know what you're using it for, right? So in this case here, when I'm trying to make those connections, so let's say, for example, this enclosure is bonded to the neutral, and I want to bond this nipple via this hub, which is connected to this enclosure, which is bonded to the neutral. In other words, it's saying that threaded hubs and threaded coupling applications and things like that are going to make a metal to metal bond. Okay. And they're okay for this application when it comes to services. Okay. And the easiest way to picture this is that riser coming into a hub and things like that, threaded hub in the top of your meter socket. That hub connects that riser to the actual meter socket through that hub. The hub has 4 screws that's connected to the meter, which the meter is connected to the neutral bar. All of it's connected together. And this is just saying those threaded couplings or threaded hubs are okay to bridge the gap, okay, to make those connections, all right? So weatherproof hubs, again, those are like the ones you see on the top. Again, this is kind of what you see, that you've seen them on the top with the 4 screws that goes in, you thread into it. And then of course you have different ones like these example, which is kind of like what we call like Myers hubs. These are just 2 of them that are from Thomas and Betts. They're weatherproof hubs. You notice they've got the seals, the grommets and everything. They may be suitable for installation of service equipment. They're listed with UL 467. All that literature should be there. If it's not, and you go pick one up from a supply house, ask them to give you the literature. You never know when an inspector might have a problem with it. But again, if you're going to use it for this application, then you need to follow the manufacturer's instructions on how to do these. Good news about these is they have a design that actually will bite down into the metal. And so that ensures that metal to metal connection with these things. Okay. I also get a lot of people that ask me, can I use hubs like this with PVC? And the answer is no. They're designed to be used with threaded entry, not to put a TA on the end of it from a PVC and change over, which I see people do all the time. These are not listed for that application. All right. The third method in a service raceway, for example, to connect pieces of metal together. In this case, let's say an elbow that has service conductors in it to a straight run, how we're connecting these together. Well, you're able to do this with threadless couplings and connectors. We're made up tight for metal raceways and metal clad cable. So again, MC cable is okay for service applications. You just have to make sure that you can, if they are threaded couplings or connectors, that they're actually listed for the type of wire method you're using, and you make them up tight, then you're bonding this piece of metal to this piece of metal to this piece of metal, all via this. And without that, how in the world would you ever do it? Okay. So it's perfectly okay. And then the fourth one is, okay, it says, number 4 says other listed devices such as bonding type lock nuts, bushings, or bushings with bonding jumpers. Okay. Now, this is where we run into a situation. Let's say we're coming into that service and we remove all of the concentric or eccentric knockouts. So basically, it would be no different than if we as a contractor went and we popped our own hole, right? We use a hydraulic KO and we knocked out our hole. We don't have any concentric eccentrics. We have no impairments anymore, right? Okay, if that's the case, it says a bonding type lock nut used with standard lock nuts on the opposite side of enclosures, no concentric or eccentric knockouts remaining at the entry. So where is this very common? So some people will come in, they'll come into a location where they come in with rigid and they'll put a lock nut, rigid comes in, they'll put a lock nut on one end, put it in, tighten that lock nut in, and then it comes into the enclosure. And then they're commonly will put another lock nut on it. That's done all the time for applications on the load side. And it's fine. A lock nut to an enclosure is fine. It's mechanical. However, in this case, it's saying if you want to use rigid, for example, and your connection is, I'm going to tell you this has to obviously be a dry location because it wouldn't work if this connection's made in a wet location. But let's say it's a dry location application where I got service coming in through, let's say, a rigid, and I bring it to a box, I put a lock nut on it first, take that into the box, and then where if it was downstream, I would put another lock nut on it and kind of sandwich it, right? And then put a bushing on it, obviously, because that means the conductors are probably going to be 4 gauge and larger. But in this case, I could put a standard lock nut on the outside to hold it against the box. You know, that's the outside. And then on the inside, I would put one of these, which would be a bonding type lock nut. So once you tighten that lock nut down, it's got that set screw that you drive in and it locks it into the metal. So not only do you have the thread contact, you have the concaved portion of the actual feet set on the actual lock nut to bite into the metal, but then you also have a screw that's required to be driven down into the metal. So it all acts as one. Okay. Now, could I do that for supply side bonding on? Absolutely. As long as I'm not dealing with any impairments. Okay. Now, what else could I do? Well, obviously I can use what's called a bonding type bushing. So I bring it in to the actual enclosure and make my connections up. And mechanically, I can use lock nuts to hold it in place, but I'm still not going to be making that bond to that raceway. So I would use what's called a bonding type bushing, put the bonding bushing on it. In this case, this one serves two functions. One, it has a smooth rounded edge. So if you're dealing with flat and larger insulated conductors, you're not going to damage the conductor. So check, got that out of the way. And then it also has the ability to have a lug set on it, because at this point, if we're using this, then we're going to have a bonding jumper. And so we need to have a location for the bonding jumper. Okay, so I could have a concentric or eccentric knockout. Okay, and I come through it and I use standard lock nuts for mechanical, but it doesn't relieve me from my bonding requirement. So then I would put on this bonding bushing and then, tighten that sucker down. And then I would have this bonding jumper. And because the root problem was it was an impairment, now I've got to have a bonding jumper, supply side bonding jumper in our case, what we're talking about, and that would be the lug for it right there. Now, this one right here is a bonding wedge. Many people refer to as the oops wedge, or the oops, I forgot to do what I was supposed to do wedge, and inspector caught me wedge. And so in this one, the bonding type wedge used with metal bushings on top of the wedge, standard lock nuts on the opposite side of the enclosure. And again, you're not going to have any eccentric knockouts remaining, so they have to remove them. Okay. Now, you might say, well, why the heck would I want to do this then if I've already got eccentrics and I messed up? Then these have the ability to also have the bushing on top, which is the abrasion, but these are also designed where you can also put a lug on these as well. Okay. So you have all of these applications. There's many ways to do it, but you wouldn't fall into this category unless you simply forgot and the conductors are already run and everything like that, and you don't want to start pulling things apart. Okay, then you can utilize this option right here. Now it also goes on other listed devices, and such as, when you see the word such as, that means that this is what we know about. There's other manufacturers, Thomas and Betts, different ones. They might have other products that are listed for this application. In fact, I have actually seen some, different types of bonding bushings. And again, those would probably fall under bonding type bushings, but there's a company called Bridgeport that actually makes the bushings that open up like a Pac-Man, they kind of has set screws on it and you open them up. That can also be considered oops type of thing. And that is very handy if you forgot to put a bushing on it for abrasion, but also you needed to do the bonding, then they can be a benefit as well. They're going to cost a little more, but again, it's probably going to be a lot less than pulling everything apart. I can promise you that. Okay. All right. So that's pretty much to cover that. I said we kind of move through these. 250.94, bonding of communication systems. Communication system bonding is required to be connected in accordance with 250.94A or B. So if you have your NEC, you can look at that. This is what we call intersystem bonding terminal locations for communication, and that's what it's for. However, in the 2017 code, we opened that up a little bit and we added a 250.94B to allow you to basically put a bus bar and bring other things to it other than communication. But if you've got one of those little communication bars called an IBT and it's listed for communication, that's all that can be brought to it. Okay, so let's talk about that one first real quick, and I'll show you a picture of what they look like. The intersystem bonding termination, called an IBT, for interconnecting intersystem bonding conductors is required to be provided externally to enclosures at the service equipment or metering equipment enclosure and at the disconnecting means for any additional building or structure. So at the one building or the service, you have it there. You can have it at the meter, okay, or you can have it at the service equipment. You can't be inside. It's got to be external to that equipment. So it's got to be a connection outside of the equipment. But when you go to a detached structure, then it's basically you're not going to have any metering equipment at a detached structure. You're going to have the requirement for the disconnect at the detached structure under Article 225 for that feeder or branch. So you would have it set up there. There's a couple things to remember that in a building that has communication systems, this is required. In a detached structure that does not have any communication systems at all, then it would not be required to have an intersystem bonding termination device. Okay, so as far as an electrician goes, I am not required to put one in if I'm taking it out to my garage and my garage has no communication equipment, and I'm not necessarily required to do anything. Okay, so but let's assume that if an IBT is used, then it has to comply with the next 4 screens. Number 1, it has to be accessible for connections and inspections so the inspector can look at it. Number 2, consist of a set of terminals with the capacity for connection of not less than 3 intersystem bonding conductors. That means, and when we say intersystem bonding, and what systems are we talking about, guys? We're talking about dish network, direct TV, those type of communications, your communication coaxial system that comes into your building. They probably going to have some. You need to have a place for them to make connections for their system, okay, to be able to make to it. Not that they actually ever run any, but you do have to have the connections in case they know what they're doing, and they do make those connections. Now, when you have this device, it cannot interfere with the opening of the enclosure for the service or the disconnection means, or even the meter. Now, I've seen some of these devices that actually look like a kind of like a claw. It's a big C, and it actually mounts on the side of the meter. And you tighten it down it has a teeth at each end, and it bites into the metal. But it's on the side of the meter, and it has its lugs on the side. And so you put that on, and you tell the inspector that's where the dish people can take their grounding electrodes and all of it they want right there, and that's done. And it usually comes with 3 terminals on it. You're done. Other ones are made a little different. They're made with an actual bus that you would mount outside under your meter or next to your panel or whatnot, and it'll have multiple lugs on it. So it's not going to be an issue of having at least 3. Usually I have anywhere between 6 to 8 to 10 lugs on there. Okay. Now, this IBT is not for you to take things like CSST bonding. It ain't what it's for. It ain't for PV systems. Nothing that is other than communication can go to this IBT. Okay, this is under 250-94A. That's all it's for, purely communication. Now, it says at the service equipment be securely mounted and electrically connected to an enclosure for the service equipment, to the meter enclosure, or to a exposed non-flexible metal service raceway, or be mounted at one of these enclosures and be connected to the enclosure or to the grounding electroconductor with a minimum of 6 AWG copper. Okay, so we're just kind of going through all of the requirements that you have to have for it. That was at the service. So at a disconnecting means, let's say to a detached structure that does have communication, assume it does, then you got to have one. It says at the disconnecting means for a building or structure, it be securely mounted and electrically connected to the metallic enclosure for the building or structure disconnecting means, or be mounted at the disconnecting means and be connected to the metallic enclosure or to the grounding electroconductor with a minimum of 6 AWG copper conductor. Okay, so that's an option. So the first one was service. This one is for detached building. They mean the same thing. They merely mean the same thing. One, you would do it to the meter of the service. The other one, you do it to the disconnecting means at the remote building. It's the same concept here, right? And the terminals shall be listed as grounding and bonding equipment. Okay, so whatever you buy has to have been evaluated for grounding and bonding. Okay, so it will have been evaluated under 467. Now, this is the one that I see the most common. Okay, it's Erico makes these. It is basically installed right outside next to the meter. And basically, one of the ways that people do this, actually, there's a couple different types. It actually gets connected right to the grounding electrode conductor. So it has some of them, you see this has a little lay-in, but this right here unscrews and it pops out. It folds back, that you actually can take this gauge, a 6 gauge, that's maybe going to ground rods. You can put this thing over top of it, lug it down, and now you've got more than enough terminals on it to meet the minimum of 3. Okay. And this would mount right there next to the service equipment or next to the meter enclosure. Now, this also could be the same thing that's mounted at the detached structure, at the disconnect, near the disconnect at the detached structure. Okay. So there's many different types of these. I've even seen some of them that don't have this nifty little case that is basically just a bar with a lay-in lug on the end. And you basically would take it straight to the grounding electroconductor, tighten it down, and then sticking off the side of it like a little flag is the bar, and it has multiple lugs on it. And that is all I've got to give, okay, to the dish people, DirecTV people, communicate. That's all I've got to provide. Now, prior to this, years ago, all we really did was take we poke out a piece of 6 gauge and we just leave it poked out, at the meter area where the other side of the wall where the panel was at, and say, there you go. You make your connection to it. Split bolt, I don't care, whatever you want. Now we have to provide them in a new installation. We have to provide them something to make that connection to. Okay. It doesn't have to be this company, but it's got to be something. Okay. There is an exception for bonding in existing buildings. So your building's already there. It says, well, in existing buildings or structures, an accessible means external to enclosures for connecting intersystem bonding and grounding electroconductors for these other types of communication systems shall be permitted at the service equipment and at the disconnecting means for any additional buildings by at least one of the following means. So this is saying, look, your building's existing. I might now be bringing communication to it later, or I might be doing something after the fact to an existing building. Maybe I'm upping the service or I'm doing something. Okay, well, first it says exposed non-flexible metal raceways is fine. So if I'm coming up out of the ground and rigid and I'm going into the panel or a meter, I'm good. Because what did we say earlier? That raceway needs to be bonded to the neutral conductor inside the meter. So that should all be done. So it's in common with it. So I'm good. I could connect to that non-flexible metal raceway, rigid, EMT, IMC. Perfectly fine. That's okay. An exposed grounding electroconductor. Hey, what if the grounding electroconductor is poking out of the building already, going to the ground rod, and it's already right there? I can look and say, I ain't got to do nothing. They got a place they can connect if they need to connect. I'm done. So if that's there, existing building has that, I'm good to go. Next, an approved means for external connection of a copper or other corrosion resistance bonding or grounding electroconductor to the grounded raceway or equipment. Okay, so I could have other means, other devices, something that's going to be copper or corrosive resistant, which would be, believe it or not, even aluminum is corrosive resistant. People think that it isn't, but aluminum is. But usually that's going to be like a zinc coated product or whatnot. Okay, so, or I could have that grounding electroconductor that is connected to the grounded raceway or to the actual equipment poking out. I'm good to go. Okay, so existing wise for electricians, as long as one of these are available, I'm done. I get to look at the inspector and say, dude, it's existing. You've got adequate area to make these connections. You ain't gonna force me to put one of those little lugs in there. You ain't gonna make me have to buy it. Okay. Now, if you want to be a nice electrician and buy one, put it in. But you have some outs here for existing building. Okay. Now, the one that was added in 2017, I believe it was 2017, is the other means. Now, the only reason for this other means is this follows a common practice that we've done in commercial a lot, and that was installing bus bars. Remember data centers? A lot of times you have equipment rooms and they'll put a big old bus bar there, big old copper bus, 1/4 inch by 2 inches wide. So it's 1/4 inch thick by 2 inches wide, and all of the different bonding comes at this one location. Okay. Well, and we do this also. There's an allowance to do this as well in 250.64 for grounding electrode applications. So why wouldn't it be okay to do that here? So if you want to put a bus and you want to make that connection to the bus, then I could actually do that and actually have one common bus. And then I can take all of my communication there if I wanted. I can also take my PV, my CSST bonding. I could take all of it right there if I wanted. Okay. So there you go. That is the allowance to be able to do this in a bus format rather than, and this is different than this. Okay. This is only evaluated for communication. This type of bar that you buy, this has been used through the code forever. And all we're doing is giving you another allowance to be able to use it here. Okay, you just have to make sure that you've got enough lugs, at least 3 terminal lugs, and you really want to make sure that you have enough for all other connections, okay, that you might utilize. When you buy these anyway, they're already going to have probably 2 levels of lugs, probably more like 10 holes on it for you to be able to make connections anyway, okay? But just so you know, it is available. You can do that. Now, the only thing I'll caution you, if it's an aluminum bus bar, be careful that it has to be at least 18 inches above the earth, okay? That type of thing. And then, of course, there's the exception to A and B, again, which says means for connecting intersystem bonding connectors are not required where communication systems are not likely to be used. If you ain't got them there, what's the point? Okay, and that's probably going to be used most at a detached structure where you're probably not going to have communication. But if you do have communication there, then you're going to have to meet the requirement. Okay, somebody have a question? Thought I heard somebody. No? Okay. All right, 250.
Paul, if I could, that's going to be a number 6 minimum, correct?
Yes. So the sizing, if you're going to run a conductor for it, then it required it to be at least a 6. Absolutely.
Okay, thank you.
You want to run 4, higher, bigger, go for it. Engineers will say 4. Code says 6. All good. All right, bonding of other enclosures. So now we're talking about bonding other enclosures. We've kind of moved off of the situation where we're talking service. Now we're just talking about bonding other enclosures in general. So metal raceways, cable trays, cable armor, cable sheathing like MC, enclosures, frames, fittings, and other metal non-current carrying parts that serve as equipment grounding conductors with or without the use of a supplemental equipment grounding conductor shall be effectively bonded where necessary to ensure electrical continuity and the capacity to conduct safely any fault current likely to be imposed on it. Fancy words for saying, look, metal is metal. Metal can hold current. We might as well bond everything. Why? Because at this point, all of this bonding that's not associated with the service, this is telling you, this is starting to where we're going to get into things like feeders and branch applications. We need a way to take these metal parts and be able to clear a fault, clear the breaker, clear a fuse, okay? So it's got to be designed safely to carry fault current. Of course, we have a nifty little list in 250.118 that says all of the different types of equipment grounding conductors that we have. So shouldn't be any confusion. We have a nice little list of what can be considered an equipment ground. The point is, all of it gets bonded together. So there's been many cycles where people have wanted to change equipment grounding conductors to equipment bonding conductors. And it's not necessary because the moment that we change that to equipment bonding conductors, somebody will say, why don't we call them equipment grounding conductors again? Because it serves a grounding function, again, voltage potential, but it also serves a bonding function. So informational note was added to say, hey, look, it does both. It does 2 different things. There's no sense in changing the name of it, okay? So it's going to stay equipment grounding conductor, and it did not change for the 2023 proposed either. Also, it goes on to say, bonding of other enclosures, any non-conductive paint, enamel, or similar coatings shall be removed at threads, contact points, and contact surfaces, or be connected by means or fittings designed to make such removal unnecessary. Okay, there are certain types of lock nuts, for example, that are designed to dig in and remove the enamel, and there's some that are not. Now, people ask me all the time, why make both? Well, I'm sure many of you probably have worked in commercial work, and a lot of the enclosures that you can buy are stainless steel or different types of metal that don't have that enamel on it. Whereas most of the residential stuff we have is baked gray with this enamel paint. Okay, so there are many enclosures that are utilized in structures today that don't have the enamel paint on it. Okay, and they are just like stainless steel, or they're just like really shiny metal that doesn't have any of this coating, and you would be perfectly okay for a standard type of lock nut that's not a biting in type of lock nut. But if you're going to use that on something with enamel, and you're not going to remove the enamel, then you're going to need to have some type of lock nut that actually bites into it. So if you've ever looked at the lock nuts, you can see a drastic difference. Look at the lock nuts that are designed to actually bite into the metal, and they'll have like a little curve on the end of it. They look like a little hook, okay, little point, whereas the other ones are just flat, okay? The flat ones are very common for use on MC connectors, use on things that you're going to use in a building, to metal boxes, because typical metal boxes aren't painted or enameled. They're just metal. But there are different types of lock nuts. Okay. And if you're not going to remove the paint from those, it could be an inhibiting factor in making sure that connection gets made, then you're going to have to remove the paint some way. Okay. I, in the day, was notorious because I was anal about grounding and bonding, had a little Dremel, and I always would before I put my connections on any of my enamel situations. That was just me, but I almost felt like the code demanded it because I know that that wasn't a good connection. And you know this too when you're testing panels, because how many of you tested things to the case and realized you had to stick it into one of the little holes that hold the panel in order to get a really good connection because you're getting to the threads. Okay, so just want to be safe. That's all we're concerned about. All right, so this is an example here where you have standard lock nuts, where this case is just a standard lock nut, and you notice that the paint was scraped off so they can have a really good connection. Okay. And this is a bonding lock nut where paint is not scraped. Over here, you kind of see the difference. But if this was a type of lock nut that bit down into the metal, then that would be okay. But this is kind of a graphic showing you one it would be cut in and one it's not. Okay. Now, if this was ground down, then I wouldn't need the type of lock nut that bites in, right? Because it would make metal to metal contact and we'd be good. Okay. And then, of course, here is an example where I have these right here being concentrics and somebody goofing. So they had to put this, or maybe this is the service. And because of these, they had to have that bonding, supply side bonding jumper. Okay. But these are feeders and they don't have to because they are able to do something a little different downstream. Okay. They don't have to have that same assured bonding. Okay. All right, so let's talk a little bit about reducing washers for a second, because we run into these awful lot in, when I ran into these the most, it wasn't because I did the knockout, it's because I let my helper do the knockout, and he went literally crazy, and they start trying to take it out. Next thing you know, they've taken the other knockouts and loosened them up, and so then I'm like, oh crap. So, but there's something that you should know about reducing washers. Reducing washers are used when the knockout openings in an enclosure is larger than the conduit or the fitting to be connected, not permitted as bonding means at services. So anytime that you have occasion where you're going to use a reducing washer on a service, you're going to have, what did we say earlier? You're going to have a bonding jumper. No ifs, ands, or buts about it. Okay. Now, reducing washers, interesting enough, are covered by the ULIQ database reference of QCRV. They're suitable for grounding and bonding if installed in compliance with the NEC. Again, suitable load side. Remove all, here's the thing that most people do not do with these. Remove all remaining knockouts and use one set of washers. Again, what we have from people a lot of times is that they use a reducing washer because they went one size too big, and they use a reducing washer, and that's not really how they were designed. If I have to do this, then I have to get the reducing washer size to fill it. That means I have to take out all the concentric or eccentrics and then use the reducing washer. Why is that? Because if you say it's a 1/2 inch and I screw up by taking out 3/4, but the overall size was a 2. Now, if I buy that and I use it, what happens is the standard feels that it's not making adequate contact to contact because of how the washers are made. So let me show this sample here. So see, if the way these are made to come tight to tight, if I had some extra rings in here, then they would not allow the reducing washer to come tight together in the application. So they truly, under the standard, believe that you should remove all of the knockouts. Now, I fully understand that probably most electricians, I can tell you right now, if you're probably knocking out a 1/2 inch hole and you knock out a 3/4, you're probably not going to go and knock out all the remaining ones in order to get a reducing washer that's going to give you the 1/2 inch, but it's a size of a trade size 2. That's what you're supposed to do. Okay. But I know people don't do that. Okay. But again, probably will work, but the standard requires that if you're going to go to a reducing washer because of something, then you have to remove all of the remaining knockouts. Not that you will, but you have to. Now, this is an example where we have boxes that are actually rated for 277, 480 applications, where you don't have to have bonding bushings or bonding jumpers in it. But because these are designed to work at a higher voltage class. Okay, so reducing washers are permitted to connected boxes listed as having knockouts that provide permanent reliable bonds. So what this means is, if I were to use a reducing washer for a box that's rated 277 without bonding jumpers, then I would not have to remove all of the rings. I could still use the reducing washer on the one that I knocked out. I could leave the other ones intact because they already were designed. These are much harder if you've ever taken a box that's rated for 277 volts and ever tried to get those knockouts out. Much harder to get those out than it is a standard box, okay? And they're designed to handle a higher level of voltage. And the segmenting of the rings will not affect its fault carrying ability, okay? All right, so 250.96b, isolated grounding circuits. Now, you're going to run into this in your career about running isolated grounds. Isolated grounds are never to take the place of the requirement for the equipment ground, okay? Never. They are permitted. And for example, if this case of this picture right here, I have my service equipment, I have a remote distribution panel downstream, and I have a piece of equipment that needs to have very little effects from electromagnetic interference or noise that can be contributed through the equipment ground through the system. Maybe something's not connected right. Maybe somebody's made improper connections and it creates things like electromagnetic interference that can affect sensitive electronic equipment. So if I'm doing that and I'm going to be invoking the ability to use an isolated grounded circuit, an isolated equipment grounding is permitted for reduction of electrical noise in accordance with the following. So in this case, here's the equipment, here's the panel, remote distribution, as my buddy would say from Colorado, subby, bruh. This would be there. And so in this case, the isolated grounding circuit or the isolated equipment ground runs all the way back to the source. Now, this is true whether it's a separately derived system, it would run all the way back to the separately derived system. If it was a separate building, it would run all the way back to the building's disconnection means. If it was a service like this, it runs all the way back, bypassing any termination in the remote panel, all the way back to the source, because that's the cleanest point in the system, right? This is permitted. But what's important is that you must still have your equipment grounding conductor system set up in place. Now, the only unique thing about this is bonded. This raceway is all bonded to this enclosure. It is on the load side, okay? But right here, the code is going to allow you to use a non-metallic fitting in order to separate this metal raceway from this enclosure. So this is being used as an equipment ground, but since we're running an isolated ground, we need that separation. So that's why you could put a non-metallic fitting in here. So there's no connection between this and this, but yet it still has the necessary equipment ground if it needs to trip an overcurrent device, okay? And this raceway is bonded to this enclosure, which is connected to an equipment grounding conductor. So if this gets energized, it'll clear a breaker, no problem. So this is an allowance for what's called an isolated grounded circuit. And why we'd run this again is a lot of times data centers or other equipment where they really are concerned about electromagnetic interference. Don't ask me my opinion on that because I always ask them to prove that it runs better without that connection. And I have done this before where I made the connection in front of them without the isolated ground and equipment runs just the same as it did with it. So again, that's just what they want. And if that's what they want, you're allowed to do it. However, you have to meet these caveats. It's the equipment is supplied by a branch circuit. Okay, got it. Isolated grounds require branch circuit. The isolation applies to a raceway containing circuits supplying only that individual equipment, which is that right there. Yep. And the isolation is permitted to be accomplished by one or more listed non-metallic raceway fittings located where the raceway connects to the equipment. Right here. Now, if I was doing this over this graphic, we might do it for the next book. I would actually make this like red or something just to have a call out and say non-metallic. Because again, but that's what we're talking about right there. Okay.
Yeah, Tesla batteries call out for that isolated ground.
They talk about
Yeah.
for that isolation. That's kind of
Yeah.
funny because Tesla, I guess the only issue with the Tesla one is that they do have an internal communication system. In other words, it talks to different things and they're worried about electromagnetic interference or something like that. So there you go. Calls it in the specifications for the product. Now you know. What else? Also, the installation of a metal raceway is required to comply with the provisions of 250 Article 250. So it looks to me like this has to be metal. Okay, so this part has to be a metal raceway in order to do that. Okay, and it says the raceway must be supplemented by an internal insulated equipment grounded conductor in accordance with 250.106D, which is that isolated equipment ground. And that's what this is right here. So think of this as that Tesla. There you go. That's the application, and they have to isolate it right there. But it's still got its equipment ground. It's still going to clear an overcurrent device. It's just a separation. What we don't want it to do is they don't want it to be tied into all the other equipment grounds, because you could have circulating current, objectionable currents. You could have improper case to neutral connections everywhere else. And we don't want them to interfere with the system. So me as a Tesla installer and me as Tesla owning the equipment, I want what's called a clean ground all the way back to the source. And that's what they're calling out. All right. Bonding of over 250 volts. Okay. So for circuits that are over 250, because everything up to this point, we were talking about applications, and we're like, well, when we get to something that's over 250 volts, do we have to do something different? Okay, well, for circuits that are over 250 volts, electrical continuity of metal raceways and cables with metal sheathing that contain other than service conductors is required to be ensured. So this isn't about service conductors, but to make it easy, anytime you're dealing with circuits that are over 250 volts, think of them as service conductors. Why? Because we can use the methods of bonding that are listed in 250.92b, okay? Except for number one, and number one was the connection to the grounded conductor. We obviously know we can't use that because these are feeders, right? It's downstream. You can't connect to the grounded conductor downstream to do any bonding, right? So that goes without saying. But any of the other methods, heck yeah. All I got to do is, if I'm dealing with the over 250, just go deal this application and I'm good to go, okay? Let's see, what is 97? Let me see where I'm at. And also, it should be said in here that we're talking about, because I'm sure somebody will ask this, that is over 250 volts to ground, okay? We're not talking about phase to phase. I mean, this is 250 volts to ground. So that would be 277 and 480 would be examples of that, not 208, things like that, okay? So let's see. Generally applies, right here. 480, 277, right in my face. It would have been nice, though, if we had to put for circuits over 250 volts to ground. That way it's nobody can question it. All right, so here we're looking at it right here. It says where standard concentric or eccentric knockouts are not at the connection point, servo wire methods are acceptable for bonding requirements. And there's a list of exceptions that you can do, but example is, remember I said standard concentric or eccentric knockouts are permitted without bonding jumpers, provided these boxes obviously are also rated for those over 250 volt applications, okay? These boxes are designed just a little different than normal boxes. They're just a little bit more beefier, okay?
Hey, Paul, good question.
Yeah.
Is that where UL 514 comes in? I've seen it written on the side of the cases that these junction boxes come in. Would that be 514 UL?
I am not 100% sure. I tell people all the time, one thing that I will say to people all the time is I am not a UL aficionado. In fact, I can't stand UL documents. I'm forced to work with them all the time in the wire and cable industry. So I can quote you verbatim those. But at the end of the day, there are so many freaking UL documents.
Okay.
The best way to check that, though, is go to Informative Annex A. And Informative Annex A, what are we asking? So yes, so UL 514B is conduit tubing and cable fittings. So yeah, that would be the standard for that. And so that's 514B. Oh, and that's probably a good exercise, guys. Anytime that you really question what a UL standard is directed towards, go to Informative Annex A in your NEC. And it says UL 514, well, 514, there's an A, a B, a C, and a D. So they cover different things. So A is metal outlet boxes. 514C is non-metallic outlet boxes. 514D is cover plates for flush mounted wiring devices. So quite a list of things that 514 covers. And I shouldn't say this, but I'm on that committee, and I've probably been to one meeting in a year. Hopefully nobody from UL is watching. I'll promise I'll start going next week.
I'm just
But-
asking because remember the old timey boxes didn't have that little, when you knock out a 1/2 inch or a 3/4 inch in these newer boxes, you always had a little connection where the knockout is attached to the box. The
Yeah.
old timey boxes were just full rings like the eccentric and concentric knockouts that we have
Yeah.
on panels. That used to be the old boxes. So now I've noticed that a lot of the cases that these boxes come in now have this UL listing on there. And
Right.
I think I was told, I was informed that that's what that UL number meant.
Well, 514 is covering a bunch of things, but it's probably embedded in 514.
Okay. God, why would you put it on the case if it wasn't? Why would they put it on the case? I guess if it wasn't.
Well, I
fire-
don't know that. Well, when it comes to these,
Mhm.
when it comes to over 250 volt enclosure boxes and stuff,
Right.
it will have to be marked as such because that is unique. And I can usually tell by the knockout because they just look way more robust, right?
Right. Mhm.
But I don't know that it directly correlates to 514. Probably something in, I'm sure that in 514 probably addresses for over 250 volts and the knockouts associated with that. So it wouldn't be far-fetched for them to reference 514 because I'm sure that something in 514 requires those knockouts be made differently
Mhm.
or over 250 volts, most certainly.
Because if it was, if you were running a lighting circuit through there, say a 277 volt lighting circuit, and it wasn't UL 514, then you may have to install a grounding bushing on that box. Is that correct?
That's correct. Yeah.
So, we can do without the grounding bushing because the boxes are
Rated.
UL rated for the installation or listed for the installation. And then I guess we're covered is what I was.
Yep. Yep.
Okay, just a question.
Yep.
Thanks.
So in building on that, to kind of build on it, is for those boxes. So boxes and closures with concentric or eccentric knockouts that are listed to provide a reliable bonding connection, the following methods are permitted. So I guess we could have just jumped to this. So threadless couplings and connectors for cables with metal sheaths are perfectly fine for those boxes that are listed. 2 lock nuts on rigid metal conduit or intermediate conduit, one inside and one outside of the box of the cable, kind of like this example here. That's okay. I guess they're showing all of them here. There you go. So there's the connection. All of these are okay as long as this box is listed for over 250 volt. 3 fittings with shoulders that seat firmly against the box or cabinet, such as EMT connectors, flexible metal connectors. They usually have a flat lip on them that connects and then the threads go into the box. Okay. With 1 lock nut on the inside of the box and cable. Again, all this is on the preface that this box is rated for 250 volts. And then of course we have other listed fittings that would be listed for this application. We're perfectly okay as well. 250.98, bonding loosely metal joining. So anytime we have expansion fittings or telescoping sections of raceways, and we use these, maybe that you have 2 buildings with the separator that actually can move, and you're going to have what's called an expansion fitting. Most of the ones that you buy already together, and they are expensive, but inside of it, they already have a strap that connects both ends. So you have the 2 pieces that move, but they are connected together. And of course, their movement's going to be very much limited to the range of the fitting, but there is a jumper that's installed inside of it. So that you buy that, everything's already taken care of. However, you might have a situation where you're using for expansion, where you're using something like an FMC or something, okay, or an LFMC, and you're using that. Say this is the building, and they required you to have an expansion and contraction connection. So some people want to use FMC. Well, bonding jumpers required for FMC if over 20 amperes, overcurrent device is supplying it, or over 6 feet in length. So in these cases right here, if I was dealing in 3/8 type, for example, FMCs, then I would have to have a bonding jumper on it, okay? And, or if it was over 6 feet, I'd have to have a bonding jumper on it. Okay. Now, bonding jumper is required for LFMC if over 6 feet long and over 20 amperes. So again, if I have over 20 or in sizes 1/2, it's actually 3/8 to 1/2. Or if these are 60 amp overcurrent devices and I'm dealing with 3/4 through 1.5, then as long as it's not over 60 and it's not over 6 feet, then this is okay. I wouldn't need the bonding jumper. If it's over that, then I would need the bonding jumper. Now, if it's not over 60 and it's not over 6 feet, as long as I don't have any small type of 3/8, half, things like that, 3/4 in my run, then I don't need the bonding jumper. Okay. So this is usually, to be honest with you, I don't see this a whole lot in expansion contraction, the use of FMC, but I do see LFMC used, and they usually will make it in a little loop or something in order to be able to allow for expansion and contraction. Okay. The key with this one is go read 250.118 and go down where you see the LFMCs or the FMCs, and you'll notice that there's rules for that. Okay. We're not going to go over all of those today, but you need to look at it because then in some cases, you're going to have that bonding jumper on it. If it's larger than what's given in the sizing allowance for it to be an equipment ground. Okay. Other thing I will set out to you is if you're putting any of these in there for flexibility reasons, because of flexibility, and I could argue this is flexibility reason, then you're also going to have an equipment ground and conductor inside of it anyway. Okay. Okay. So this is where they're using, this is the equipment ground, and this is the equipment ground, and they want to use this as the equipment ground. They can under the limitations of 250.118. If they meet those limitations, fine. If they don't, guess what? They're going to have a bonding jumper over it. Okay. Especially if they use this raceway as the equipment ground and now they can't use this, then what are they going to do? A bonding jumper required through or around the FMC if the circuit conductors have greater than 20 ampere overcurrent device in it. In this case here. So just go read those rules. They're not overly complicated, but it depends on from FMC and LFMC, they're slightly different. Okay. In this case, this is FMC. So obviously the size of this thing, this is going to be over 20 amp circuit. So it's going to have a jumper on it. And I don't know that I see one. So, but maybe they ran an equipment ground inside of it. Who knows? Who knows? All right. Hazardous locations. We'll go through this one real quick so we can get to the end of our topic today. Bonding hazardous locations, regardless of the system voltage. Okay. For hazardous locations, when it comes to bonding, I don't care what the voltage is. Okay. We got our equipment ground connections. We got to make all our normal connections, but this is what it says about hazardous locations. It says bonding is required of non-current carrying metal parts of equipment, raceways, and other enclosures in any hazardous location defined in Article 500.5. That should be going out without saying because we do have to bond all non-current carrying metal parts of equipment anyway. But in this case, it's making it very clear that the voltage is not the key trigger here. Now, when it comes to bonding, it's telling us again, any of the methods specified in 250.92B2 through 4 is permitted. Why is that an important statement? Because basically it's telling you what? I need you to do it like it was a service. I need you to do it at a little higher level than what you would do as a feeder normally. So by making this reference, it's saying, hey, I'm giving you a list of things you can do. But notice it doesn't tell you can use B1 because again, that's a connection to a grounded conductor and we're not allowed to do that downstream. Okay. But it's letting you use it, these other allowances here. Now, bonding is required even though equipment grounding conductors are installed. That's a huge one right there. Even though I ran my EGC and I'm thinking I'm good. When it comes to hazardous locations, no, there are requirements for assured bonding. Now, good news for you and me, most of the applications in a hazardous location are all threaded anyway, and there's different hubs that are threaded into, and the boxes are all making threaded connections anyway. So this should go without us having to worry about it. But you need to know that that additional application does need to take place. Okay. Specific requirements are in. So if you're wanting to learn where they are, and again, many of you probably don't have anything to do with hazardous locations in your entire career, But if you wanted to look at the requirements for this bonding, it's pretty simple. Dot 30 is the section within 501, 502, and 503 for all of those applications when it comes to the bonding. Okay, so again, just remember dot 30 when it comes to this area. That can be confusing because we know that dot 30 in other areas of code means something else. But here, that's where, you know what, and I'm going to double check that just to make sure that the author did not make an error, because I don't want people to think that dot 30 is any different than anywhere else. So I'm going to go look real quick, as you should do. And I'm going to look at dot 30 and just make sure that that is the, yep, okay, it is. Grounding and bonding, sweet. All right, there we go. So the next thing I will tell you is that this is covered extensively in Unit 8 of this grounding and bonding program. And it is probably my favorite program of all the programs that I have. All of the intro videos are by me. I did a contract with Cengage to do all those for them. So the grounding program, I just want to tell you, those that are interested that aren't in the bundle, that don't have it, use this code right here. You get $100 off for attending today's webinar. So use the dollar symbol 100 off to get your discount. It won't be activated until after this course. But again, if you're interested in the grounding and bonding course, there you go. I'm going to give you $100 off just for attending today's webinar. All right, now we're getting into these jumpers. Now, this was kind of the reason why I went on the other stuff, because I said I wanted to fill up a good 2 hours of knowledge here. So equipment bonding jumpers, the material. What can I use for an equipment bonding jumper? Okay, I can use the requirements to be copper or other corrosive resistant metal. Aluminum would be fine. Permitted to consist of a wire, bus, screw, or other similar suitable conductor. And remember, when we say equipment bonding jumpers, they fall in a bigger scope, right? So equipment bonding jumpers also encompass supply side and load side bonding jumpers, because all of them are bonding equipment, right? So this is just talking about what types can I use. So this, in this picture right here, the bonding jumper permitted to be copper or aluminum, and maybe a wire, bus, screw, or similar suitable conductor. And the statement to the screw very much leads credence to main bonding jumpers, for example. That can be a screw. Does not have to be a wire, but it could be a wire. The difference between a main bonding jumper being a wire versus a screw is if the screw, I ain't got to do jack. If it's a wire, I still got to size that sucker, okay? So again, I got to do a little more work if it's that. But those are the type of materials that we can use. Now, as far as attachments, making the connections, equipment bonding jumpers are to be attached according to 250.8, which 250.8 is such an important list item format of all the different connections, pressure connections, self-tapping, as long as it makes two thread contacts, covers a wide variety of applications for making those connections. Okay, so you have to follow 250.8. Now, a couple cycles ago, there was a misconception that you had to pick one and stay with it. I could use a bunch of those different methods, 250.8, in my installation. They don't all have to be the same. I could use lugs here, there, so I could use different ones, okay? Somebody had a question? I don't read chats during the webinar, so if you got a question, just open it up and ask me.
I was just apologizing for being late. The damn Central Time got me again.
Oh, did it?
Yes.
No worries. It'll be available for rebroadcast, so you can watch it later.
And I work in Central Time.
Oh, there you go. That's even bad. That's even worse. Now you have no excuse. That's almost as bad as Jay not reminding me to record. Oh, that's right. He did. Never mind.
Jay?
He did.
Did he remind you today?
Yeah, he did.
Good.
So we're good. And I'd already started. So, all right. So in this case, the 250.70, for those that didn't know, that is giving us a list of applications where we're connecting to the electrodes. Okay. So many different ways to do it. There's just some shown on the screen, different types of lugs, different type of connection methods, barrel lugs, splices, connections, crimping, all these type of things are available. Just make sure you know that 250.8 is dealing with those connections. 250.7 is talking about those connections to the actual electrodes. And again, I can be honest with you, knowing manufacturers, how they do, all of these products are going to be listed for their application if they're being sold as such. All right, so now let's move on to our sizing of supply side bonding jumpers for a single raceway, just one raceway, okay? So we're sizing one raceway. Now, size in accordance with table 250.102C1. So all of you should go to 250.102C1 because we're going to be working in that area. based on the size of the supply conductors. Okay, so it's the first general rule. Number two, the larger conductors, for larger conductors than in the table, size not smaller than 12.5% of the largest phase conductor. That's an important statement, because if we have three sets of ABC, ABC, and ABC, and I'm doing each raceway, I'm not going to add the volume of A, B, and C together. I'm just going to take A, okay, and I'm going to take all the A's rather than A, B, and C, A, B, and C, A, B, and C. You with me? So again, kind of the concept, you're going for only think about one phase. Don't be thinking about A, B, and C. Just say, okay, I'm going to stick to phase A, and that's what I'm going to use. The only time that this wouldn't be right is if A phase is different size than B phase is different size than C phase, which is a abnormal thing, and it's usually not going to be that way because of division of current. But just remember, we only need to use one phase, okay? And if it's a parallel, we use that one phase from each of the parallel runs. With me? Okay. Now, we're going to look at a graphic here in a second, and it's going to be noted with some A positions and B positions. Okay. Now, A positions, the size of the supply side bonding jumper is selected from table 250-102C1 using the size of the ungrounded supply conductors at that point of the connection. And then B is the size of the supply side bonding jumper selected from table 250-102C1 using the size of the largest set of ungrounded conductors at that specific point of where we're making the bond. Okay, so kind of setting the tone for the graphics. So here we go. So in this case right here, our familiar setup we had from earlier. Here's our CT. Here is our gutter. And I'm going to say this is an auxiliary gutter because of its positioning for wiring. But again, if it wasn't mutually connected here, then I could argue that it's a wireway because it's, you know, different. But right now it looks like it's trying to add additional wiring space. So I'm going to go with a gutter. Not that that matters. It's still metal, so it's irrelevant for bonding purposes. And here are our service equipment. Okay. And in this case, they're using a common grounding electrode conductor setup with a common, and then these are grounding electrode conductor taps. Okay. And in case you didn't know, this right here is sized based on the size of these conductors, and these taps right here are based on the size of these conductors. Not really for today's episode, but we will be having a webinar coming up where I talk about all those little nuances of connections. All right, so here we're at now. So all of these A's are sizing this supply side bonding jumper only based on that point, and it would be for these conductors right here. So while there's an A, B, and a C in here, we're just using A. And then we would size it, and we go to table 250-102C1, and that's what we would size this jumper for here. This up here. Now, since we're bonding this entire enclosure, that means this bonding jumper is seeing activity from both of these. Since we're only bonding this because there's only one in it, and we're bonding this one because there's only one in it, this bonding jumper sees both of these raceways. Both of these sets are in here. So we size this one based on the size of both of these. Okay. So for sizing, it would be ABC and ABC. We just simply take 1A and 1A and we add them together, and we go to 250-102C1 to do that. Okay. Now, right here, we're bonding from this enclosure to this enclosure. And this is how I do this to keep it very simple for people because they get lost. I am wanting to bond this enclosure now. So how many wires is this enclosure seeing? Well, it's seeing two A's, two B's, and two C's. So I'm going to take the A's. Okay. I only have to take one phase set. So if this was 500 kc mil and this was 500 kc mil, that will be 1,000 kc mil. Then I'm going to go to 250-102C1, and I'm sizing this bonding jumper right here on 1,000 kc mil. So this one would be on 500s. If these were two 500s, let's say, this would be on the 500 size. This would be sized based on these 500s. This would be sized on these two 500s together. So this is 1,000. This enclosure here is seeing all of the sets. So this one right here, to bond this to this, is based on two 500s right here. Now, coming down to this nipple, which is a separate piece. And here's the other way that I break this up for people. Treat each thing separately. This is one component. This is one component. This is one component. And this is one component. Each one of them have to be bonded. Okay. So because the rules for service conductors that we saw earlier is the reason I went over that, is because I couldn't use things like standard lock nuts here. Okay, so I'm going to use a bonding bushing. So this one is sized right here based on the conductors that are in this raceway. Same with this one, raceway. Pretty simple, right? And this enclosure is getting bonded based on this conductor here, which is actually the main bonding jumper that's sized, and it makes a connection right here to the actual metal enclosure, okay, which is directly connected to the grounding conductor. So everything's bonded. This is bonded to the neutral. This nipple is bonded to the neutral by this supply side bonding jumper. This enclosure is bonded to the neutral by this supply side bonding jumper, which is bonding it to this enclosure, which is bonded to the neutral through this supply side bonding jumper. And this raceway is connected to the grounded conductor by this bonding jumper, which is connected to this enclosure. All of these terminations here are provided in accordance with 250.8. All these are, okay? It's covering all of those. And of course, these connections are all provided by other aspects of the code, and connection to the electrode is going to be by 250.70 type of lugs, okay? So all makes sense in how we come together, okay? So now let's look at how this would work. So let's say we have supply side bonding jumpers for 800 through 2000 ampere services or separately derived systems. It works the same way, okay? Supply side bonding jumper, also from the secondary to the first overcurrent protection device of a transformer, same way. You size it based on the derived conductors. Don't overcomplicate it. Whether it's a service or secondary conductors that are derived from a transformer, you're basing them on the size of those derived conductors, no differently than on a service. We're basing it on the size of those service conductors. Don't make it overly complicated. It's exactly the same. Even though those secondary conductors are not considered service conductors, they're feeders or secondary conductors from a transformer. We're going to use them the same way we would if they were service, okay? Same concept. So let's look at this one. So let's just say we have an 800 amp service. And the service conductors coming in, we've got two sets of 500. So the total circular mill for that would be 1,000 kc mill, right? So if we were to go look up 1,000 kc mill, what would we have? So let's go in our code book and let's go and look under 1,000 kc mill. And what does it say? 2-aught. Okay. So there's a 2-aught. Okay. All right. And then of course, parallel for each one of these raceways, if we were doing a supply side bonding jumper for each one of those raceways, then it would be based on 500, right? And that if you look at 500, it says it would be 1-aught each. And the reason it says 2 is because that would be where you ran an individual one to each raceway. Okay. I ran 1 to 1, 1 to other. Now, the funny thing about this is that the standard allows me to do this 2 ways, guys. If I want to run one supply side bonding jumper and loop it through both of these raceways, I can do it. But I have to take this total area to do it. So that means that would be a 2-aught that I loop through the 2 lugs at both of the raceways. Sometimes your lug might not be big enough and it ain't going to receive a 2-aught. Now, this is probably a pretty benign application, but look at the one that's 2,000 amps and you're going to see why that loop, this daisy chain method is not going to be real conducive for us in a minute. So this one's pretty simple, right here. Now, what about 1,000 amp service? So I've got 3 sets of 400 kc mill with a total circular mill of 1,200. That's again, adding all those up. And the minimum area for the bonding jumper is what? 150,000 circular mills. So how did we get that? Where's my calculator at? Because God knows I'm not going to try to do math in my head without it. I'm too old for that. And I did not stay at a Holiday Inn Express, so I'm going to do it this way. So 1,200 times 12.5 is going to give me the 150,000. Okay. So I'm going to go to chapter 9, table 8, find me a conductor. I don't need to do that at this point. You know, that's my total area. So I'm going to go to the chart here and say, that's the approximate area of my bonding jumper. So what size do I need? for that? Well, let me see here. I'm going to go to Chapter 9, Table 8. Go with me. You have your code book. Chapter 9, Table 8. It's got to be at least 150 kc mil. What size here we got here? Let me.
Looks like maybe a 3/0.
Okay, so let's see here. Yeah, because 133-100 is for 2/0, and that's not going to work. So the next size up is 167,800. That's a 3/0. So there you go. It's got to be up there. So I've got to have a 3/0. Okay. So now if I wanted to use just one supply side bonding jumper and go from my grounded terminal bus and then take that conductor, that 3/0 down and go through the first bonding bushing and then loop to the next bonding bushing and then loop to the next bonding bushing, I can do that. The code allows me to do that. But I got to make sure that lug can actually handle a 3/0. And there's where you start getting into trouble because the lugs start to be a little bit, even the lay-in ones don't work when you start getting above like 2/0. If you're familiar with working in it, they start to get a little bit iffy at that stage. And then somebody might make some bigger ones. But again, the other thing is, do you have this larger size conductor just laying around where you probably have some of these smaller sizes for other applications in the project, okay? Rather than have to go drag out some of these things. Anyway, so if I want to run individuals to each one of those raceways, just from the grounded neutral bus to each one of these bushings on each one of those raceways, then it would only be a 1/0. And why? Because it's still based on the conductors that are in that raceway. And a 400 falls in over 350 through 600. So that's still a 1/0. So much easier to run a 1/0. I know I can get a lug for a 1/0. Perfectly okay. Now let's get a little bit bigger. 1200 amp, 4 sets of 350s, 1400 needs a 175,000 circular mils. Again, that's 12.5% of that. And so that would be go to Chapter 9, Table 8. And for 175, it looks like I'm going to need a 4/0 because 167,800 for 3/0 is not going to cut it for me. It's got to be at least 175. So I got to jump up to a 4/0. That's 211,600. Okay. So if that's the case, can I run from my grounded neutral bus to each one of those raceways that I'm bonding with the service conductors in it for supply side? Yes. Can I do that? Absolutely. Do I have to worry about whether the lug can handle it? Absolutely. So let's say my lug can't handle it and somebody's freaking out. Oh my God, I failed inspection. No problem. So I can run 2 gauge to this because it's based on 350s in each raceway. So if I go to 350s, it says over 3/0 through 350 allows for 2 gauge. So man, my conductor is getting smaller. Okay, because I'm paralleling, and so the conductors can handle more current in a parallel application. So now I can run a 2 gauge copper from the grounded bus to each one of my raceways individually. Okay, so that's called an individual supply side bonding jumper. Okay, so I'm running it individually to each one, and it only has to be a 2. Now go to the 1600, same scenario, 5 sets, 1750 kc mil. It's 218,750 circular mil. It's 12.5%. So that means it's got to be what? Well, if you go looking at it, well, the last one that's in the 4/0 here is 211,600. Then the next thing is 250 kc mil. So you can no brainer here. I got to go to a 250 kc mil, and that would be if I ran 1 through it, daisy chaining it, or I ran individuals. I could go with the 2 again. Trust me, I'm going to be using that 2. I don't care if I got to run 5 of them, much better than I'm going to be trying to bend around that 250. All right. And then of course, the 2000 amp, 6 sets, 2400 kc mil requires 12.5%, requires no less than a 300,000 circular mil. So that's 300,000 kc mil. So again, in that scenario, I'd have to be running a 300 kc mil through all of these lay-in lugs. And I don't know that a lay-in lug will accept a 300 kc mil. Okay, so chances are I'm going to run 6 1/0. And where do I get the 1/0? Because it's based on the 400 in each raceway. Yeah?
Well, yeah, we do 350, 500 all the time at work.
Say that again.
We do 350 and 500 at work all the time. That's our common size.
You actually have lay-in lugs that accept that?
Oh God, I want to say yes.
Okay, I have not seen any. What I have seen is people use a lug that it fits in, but when they go look up the listing of the lug, it's not allowed to go to that size, but yet it still fits in there. But they'll notice that when they turn the screws down to bind it, it's only engaging one screw, one thread, and it's not adequate. In fact, if it expands or contracts, I have seen cases where that lug actually falls out. So I'm not saying they're not available, but I'm saying the only time that I would do something like this is if I was already running 350s and 400s and I already had a scrap and I would have had to go specifically buy some extra 250 or something. As long as my lug can handle it, then I might use the bigger. I might even go bigger than I need, only because I got some scrap left because of what I ran for these. And I might have cut it off at the end before I terminated it. And I'm thinking, crap, I'm not going to waste it. I'm a thrifty electrician. So I'm going to use it, and I might use that as my bonding jumper if it's available. Okay. I'm not going to go out and buy it specifically for my bonding jumpers when I can probably have more applications where I would use 1/0s and 2s. But again, as long as you know that you have ways, different options, have at it. If your lug, just make sure you verify that lug can handle it, not just because it fits, but that lug is rated for it. If it is, go for it. Absolutely. Absolutely. All right. Now, that's an application. Oops. So now let's talk about the typical applications that we run into when we're dealing with size for parallel conductors installed in 2 or more raceways. Okay. And I should tell you this. If we had a raceway, let's say we have a trade size 6, pretty good size raceway. I could have multiple sets in that raceway. Now, of course, once I get more than, more than 3 current conductors, I got a bunch of crap I got to worry about, but I could put them in that raceway. So when I'm sizing a bonding jumper to a single raceway with multiple sets in it, again, I'm still only going to take just one of the phases and add them up. So if I had 3 sets of 500 kc mil in there, okay? And so it would be just the A's. So it'd be 500, 500, 500. That would be 1500 kc mil, 12.5%. That's the size of my bonding jumper that I would take to that single raceway, okay? Again, so that was just one raceway, okay? So what I showed you was how to do the singles and then how to do parallels. But we need to look at 250-102 C2 because we talk so much about C1 all the time. Everything we reference is 250-102 C1. You never hear people talk about C2. And the reason is C2 ends up sending you to C1 anyway, but it's good to talk about it. So if the ungrounded supply conductors are paralleled in 2 or more raceways or cables, and an individual supply side bonding jumper is used to bond these raceways or cables, just like what we did. Remember the daisy chain method? It says the size of the supply side bonding jumper for each raceway or cable is required to be selected from table 250-102 C1 based on the size of the ungrounded conductors. A single bonding jumper is permitted per C1. So that's saying that, again, I can have one daisy chain, but I'm going to have to take in accumulatively the size of the ungrounded conductors if I want to do that. So we saw how to do that in this exercise right here, okay? So let's look at another example. So here's some examples here. Now, these are service conductors, say, coming in, and they're just simply slamming to a bus. And this might be an exterior bus extender or a busway or whatnot. So here's here are the raceways coming in, okay? And coming in, let's see here. We got 2 methods of sizing the supply side bonding jumper for metal enclosures and raceways that contain service entrance conductors. And supply side bonding jumper or supply side, again, all based on 250-102C, all based on that. So it's not brain surgery here. So here's your raceways. Let's focus on these raceways. Here, 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 okay? And I will tease the author that his doesn't seem like he identified his conductors properly, okay? He's put a little tape on these fat mamma jammas, but we'll have a side conversation about this, and I'm always looking for opportunities to dig at him, so we'll do that. So in this case, supply side bonding jumpers sized from table 250-102 C1 are based on the service or separately derived system conductors for individual conduits. So conduits. So here, individual one, individual one, individual one. How are these sized? This one is sized based on this raceway only. And we'll just say that this is a 500 kc mil. So all of these are 500 kc mils. So this one right here is sized based on 500 kc mil. Okay, that's the largest phase in the raceway. Again, don't try adding them all up. I have people that do that all the time, and I'm not sure why you would do that. Okay, but here, same thing for this one, sized on this one. So this is probably an A, B, and a C, and A, B, and a C, and A, B, and a C. So again, individual, you have that option. And then down here is what we talked about, daisy chain. And that daisy chain, I'm going to have to add up each of these and do the 12.5%. So sizing supply side bonding jumpers in this method, where I want to use one wire, okay, table 250-102C1 or 12.5% rule, okay, if the total area of the service or separately derived conductors exceed 1100 kc mil copper or 1750 kc mil aluminum. So then I'm going to use the 12.5%. What I want to make it clear, guys, in looking at this so that I can throw a picture to you, say these are service conductors, or these could be secondary conductors from a transformer. You're still sizing these jumpers the exact same way. Okay. All right. Now, equipment gets a little easier here. Equipment bonding jumpers on the load side. Again, we're all familiar with 250-122. That's how we size equipment grounding conductors. We're going to have a lot of exercise here that's going to tell us that's exactly how we size equipment bonding jumpers. Okay. So look at this enclosure here. And I will tell you that this enclosure right here would be a violation under the 2020 code if this was a service. Okay. If this is a feeder, then it would not be a violation, because feeders are protected by an overcurrent device upstream. So that rule of the 6 disconnects in a single cabinet doesn't apply to feeders. It applies only to services. Okay. So we'll just, for craps and giggles, so I can't find a second reason to tease the author, who's my buddy, I'll say this is a feeder panel, and these are load side connections off a feeder panel. We'll do that and save face on that. All right. So, and we'll say that it probably is because it looks like I've got a neutral, and it looks like I've got equipment ground, and it looks like my neutral's isolated. So whoop, whoop, he's all right. He's got a feeder going on. All right, now, so let's look at it. Size 250.122. This need not be larger than the largest circuit conductor, but not smaller than 14. So your equipment bonding jumper never needs to be larger than the largest circuit conductors, okay, in this scenario. It needs to be larger than that scenario, right? There is an exception to that rule, which I got changed for the 2023, or not changed, but clarified, which still requires you to apply the 12.5% rule anyway, but in a certain application when it comes to larger conductors than what the tables give you. But that's not in the code yet, so we won't worry about that.
Question, Paul.
Huh?
I have a question.
Yes.
So why the bonding jumpers?
These?
Yes, sir.
Okay. Because if you see this is an open bottom.
Oh, okay. All right. Gotcha.
Yep. This is an open bottom.
Okay.
So if you have an open bottom gear, then you still got to bond these raceways, right? Good point,
Yes,
though.
sir.
Very good point. It probably would help to add open bottom somewhere, but of course I always can tell because the raceway continues through and the bushing is isolated up higher and you don't see any threads. That tells me that's an open bottom, but you're right. So you don't have one here.
Right.
But you have one here because this is an example of an open bottom piece of equipment. You still remember the general rule? We still have to bond to all metal. So that's why these bonding jumpers are required. So that's a good question. Good example, in case anybody didn't notice. Now, sizing the equipment bonding jumpers on the load side of an overcurrent device in 250-102D, distribution equipment supplied by a feeder. Neutral is isolated from the enclosure. So he kind of got it all. We should have looked at that, and that would have let us know what it was anyway. So there you go. This is isolated. And so this is what we'll be focusing on, right? This is the individual equipment bonding jumper. Now, let's talk about how this here's how for a motor. Okay. So one thing I should tell you real quick is in bonding these raceways here, if you're going to run the single, and I'm going to point you to, hold on here so I can point you to what, make sure real quick, because he doesn't have it on screen. Go to 250-102D, and you'll notice it says, and this is the charging statement of D. It says equipment bonding jumpers on the load side of an overcurrent device. It says the equipment bonding jumper on the load side of an overcurrent device shall be sized in accordance with 250.122. A single, and this is what he's doing here. It says a single common continuous equipment bonding jumper shall be permitted to be connected to 2 or more raceways or cables if the bonding jumper is sized in accordance with 250.122 for the largest overcurrent device supplying circuits therein. So in this case here, we've got a 350, 300, 200, and 250. He's going to be sizing this based on this 350. Yeah, these are going to be oversized for these, but if he runs a single one, that's what it's got to do. There's no exception to that rule. Uh-oh, somebody got some NFPA goodies. All right, that's what I'm talking about. Boxes of goodies. All right. So
Cool.
let's talk about a motor. So a 2 horsepower, 230 volt motor, we would go to table 430.248 FL. Actually, that should be FLC as 12 amps. I will tease you about that. The minimum circuit conductor size is 12 amps times 125%. That's what it says for single conductors in 430.22A. In that case, we go to table 310.16, and it would be a 14 gauge. Again, this is motors, so we don't worry about the small conductor rules. Okay, we're not really worried about that anyway. The overcurrent is permitted to be up to 250%. That is the ground fault circuit GF ground fault short circuit protection requirements. So that case up to, we'll say a circuit breaker, up to 250%. So that 12 amps times 250% equals a 30 amp maximum overcurrent device. Perfectly fine. Now, that means that it's a 30 amp device. And we're not really showing you this method. I have other videos for that, but we're showing you he had to determine what the overcurrent device was in order to determine what the EGC has to be. Okay, so that was just the exercise we had to do. So he determined that it was a 30 amp overcurrent protected device based on 430.52 for short circuit and ground fault protection for a motor. And that means that he went to table 250.122 based on that 30 amps, and it's got to be a 10 AWG. Okay, now, why do we say that statement earlier about it not having to be larger? It says it's not required to be larger than the 14 gauge. Okay, so he had 14 gauge copper conductors. Many people will say, well, if you have to base on the overcurrent device, then he should have 14 gauge for the power conductors and a 10 gauge for the equipment ground. Well, that rule was so important because it says that it doesn't have to be larger than the circuit conductors. Okay, so I can see that for those that take exams, that's a kind of a low-hanging question on an exam. What size? You can bet they'll give you 14, 10, 12, give you everything. And it never has to be larger in this case, in this example, than the power conductors, which are 14 gauge. Okay. Now we're talking about these equipment bonding jumpers on the load side. They can be either outside or even inside of a raceway. Okay. So if you've got something like these flexibles right here, got some flexible type of wiring methods here. We've got, so it looks like liquid type, flexible, metallic conduit, maybe. Bunch of different types. This looks like an FMC right here. So it says install, you can install this equipment bonding jumper can be installed on the inside or outside of a raceway or the enclosure. Okay. Or installed outside. The length generally limited to not more than 6 feet. Okay. So you do have an allowance on poles outside applications to go further than 6 feet. But for most applications inside of a building, these bonding jumpers are going to be limited to 6 feet. Okay. And this is an example of one. So this was a raceway that looks like it was being used as an equipment grounding conductor. Okay. And on this side, it looked like the raceway was, but then they used some flexible and it didn't qualify. So they had to put a jumper on it. In this case, they chose to use it on the outside. Okay. And it's okay. Just make sure they've got proper connectors, proper fittings, and make sure they size that jumper correctly, and not a problem. Metal water piping, 250-104A. Not really, we pretty much at this point covered our topic for today. So I'm probably Probably not going to go into water pipe bonding because we pretty much, that's just a bunch of additional. Yeah, as you can see, I have quite a bit on water pipe, and we're almost at the time. I've got 5 minutes, and we've covered our topic for today. That will probably be for another episode or something like that. So, any questions that you might have about supply side bonding and load side bonding jumpers, or anything that we might not have covered that you have questions on?
Hey, Paul, quick question.
Yes, sir.
All these images are originally from the book. Correct?
Yes, absolutely. So this is all part of our grounding and bonding course. And the course is based on the book. The difference is, again, in the course, there's, again, quizzes and checks and balances to make sure that you truly understand these concepts. So a lot of the questions at the end will make you think, did you really understand what you just read? And that type of thing, because I'm a big believer of reading stuff. I do a lot of videos. Everybody knows that. I do a lot of podcasts. But my biggest belief in people grasping things is being able to read it. And then after you read it, comprehend what you just read. And that's important. The moment that you can read it and then you pull away and you can comprehend it, then you've made a breakthrough. Okay. So
The
when you open
question,
the book, is there answers to this book, like an answer booklet, or no?
No, well, the course is actually graded by me. So I grade your work.
Okay. All right.
I grade your work, and that way I can be as polite or not so polite.
Oh.
However, but everybody knows I'm always so polite. So, and so I want to make sure that you get it. But again, believe it or not, that's a lot of information. We usually teach just that, a week-long course just of those concepts, because we usually have all the pieces that we can show people and they can put their hands on. COVID kind of killed some of that traveling and doing those type of things. But this is the concept of the little mini webs where I'm going to be doing the 2 hours to try to cover specific topics. And so hopefully you got something out of it, again. And I felt like adding the first part because, again, it's kind of hard to understand why we're doing supply side bonding and all this if you don't understand the principles of why we're doing it to the equipment and all the stuff that we do. So it's felt like it kind of goes hand in hand with all that. But anybody other questions?
yes, Paul,
Yes, sir.
out in the oil field, we use the Myers hubs a lot.
Mhm.
And we don't, and though we could get the ones that have the little green screws on the ring, but we seldom, we hardly ever do them.
Yeah.
Wow.
So the difference is you can use Myers hubs are used a lot of times even in a feeder application, right?
Yeah.
Then it's probably not a concern about its listing, right? Because of the design. The difference in the two is Myers types of hubs that are designed to be used with service applications have to undergo a little more testing. So you've got Myers hubs that have the screws like you say, and you have some that don't. Chances are, if you look at the evaluation, you'll see that the ones with the screw are designed to work with service applications, and the ones without it are designed for feeder applications, which is fine. But they make a bunch of different kinds, and you just have to check with the manufacturer.
We had two 350s PLX, two 350 PLX come into a disconnect, a 600 amp disconnect, and they were eccentric knockouts. They went all the way up to 4-inch, I think, and we were using 3-inch. And I told the foreman, I said, you're gonna have to put bonding bushings on these.
Were they service
It was
applications?
service. It was for the service, right? It was
So any impairment at all is going to require a bonding jumper.
he wouldn't do it. He said that, well, you got a Myers hub, you got a Myers hub on there. The armor core itself is going to be bonded. Like, whatever, man.
Well, the
Right.
thing about it, the only way we could get around this, right, is to say, okay, so that takes us back to 250.92B, right? And we have that list. And basically, it'll allow me to use other listed devices in other applications there's a bunch of different things here. For one of them, for example, it says, where is it? Okay, it says connections through threaded couplings or listed threaded hubs on enclosures if made up wrench tight. Now, the problem with that is anytime we have impairments, then we have to use a bonding jumper. If you remove all of the knockouts and you're using a proper size fitting for the knockout, then you do have other allowances in here that you could use. Okay. We only need the bonding jumper if it's an impairment. Okay. Because remember I said one of the other options we could use was a bonding type lock nut. So the question really comes down is if that Myers hub is listed for use as service application bonding, and you remove all of the knockouts and you choose and you use the right size, then you'd be okay without any bonding jumper. However, if you use a Myers hub and you knock it out and you're using a reducing washer, then you still got to use a bonding jumper because you can't use reducing washers for service applications. So it really depends on what. So it's really a benefit for the industrial guy who has a punch kit to just punch everything out. Get rid of the reducing, get rid of the eccentric, concentric, just punch out the right size. Then you can use things like bonding lock nuts and things like that and really saves yourself a lot of grief. But, that type of scenario. So, and also in his case, if he was coming into the equipment with a hub, threaded hub, then again, that would be okay as well because that has nothing to threaded hub like a top of a meter. That's got no knockouts. That's just a hub that bolts to the equipment. Then he'd be okay too. But the only way I could use a Myers on that is if I had absolutely no concentric or eccentric knockouts and I was coming straight into the properly sized hole. And that Myers was rated for service bonding. If it was, then I'm gravy. If it's a feeder style, I'm screwed. That type of scenario. Although probably 98% of the people inspecting it probably wouldn't know the difference between the two. So I teach inspectors to look for that little screw. If it's on the service side and they use it, look for a little addition to a Myers hub that would allow it to be for service rating, or ask them for documentation if they're in question, that type of thing. And yep, and I don't know how many times I see hubs on top of equipment where they'll put a TA or pull something into the top of a hub and they'll bring PVC into a hub or into Myers hubs and things like that. And they're not listed for that, but they do it all the time. I see it. Just saw one the other day. And the guy sent me a picture of it. He was extremely proud of his install. And then I noticed that he had PVC connecting over to it. And I didn't have the heart to, he'd already got his green tag and everything was done. So I was like, I'll let it go. But so I told his helper so he could rag him. But other than that, any other questions?
You had a picture earlier, Paul, with a panel that had like 6 300 amp breakers in it.
Yeah, the one for the last one I did, which was the for the load application, the 6 of them. Yeah.
You showed the bonding jumpers for all the raceways on the bottom, but the feeders at the top. What was the exemption there? Because there's no exemption. It's a feeder. Feeders allow you to use regular lock nuts. You can do regular lock. The reason the bottom was done is because it was an open bottom and there was no connection of those raceways to the enclosure. They were isolated in the bottom. So you still have to bond those raceways. So how do you do it? They're poking up in the bottom. Okay. It's maybe sitting on a slab, on a concrete pad. How do you do that? Well, you put a bonding bushing on the end of them and then you put the lug on it and you loop it. Or you do the smart thing, you do it in PVC and you don't have to worry about all that bonding, that type of thing. So, but that's why that one was done that way. But the ones at the top, that was just standard lock nuts, standard application. They're okay. Lock nuts are fine, except for service applications. Then you have to have, you have to have difference. You have to have the bonding type lock nuts. Okay, which the only difference is usually all of those have a little angled teeth and they also have a screw that drives in. It's a big difference. And it actually drives into the thread. It doesn't drive into the metal, it drives into the thread. So any other questions? Hopefully y'all got something out of it and felt like it is worthwhile and you got something. So other than that, if I got no other questions, I will say
peace out to everybody. I appreciate you all. And I don't know what next month's mini webinar is going to be at yet. So I'm taking recommendations and suggestions, but if I don't hear anything, it'll probably be another one within the grounding scheme, that type of thing.
Appreciate you.
Sorry, it's late.
All right, everybody. Y'all all take care. And we'll see you next time. And hopefully you'll see us tonight on Electrician Live with my co-host, Jay, the Basement King Grundberg, at 8 p.m. Central Standard Time over on the YouTube channel, youtube.com/masterNEC, or you can watch it over on electricianlive.com as well, but you don't get to comment over there. So join us over on the live stream. Look at the man. It's got all his stuff. Look at that.
Keep
Got
going.
his order from NFPAs.
Creation for every catalog.
Look at all that goodies he got.
Or what else can I? Let's see right here.
You know what? I think he should just buy us all books. Look at that. He's got that. He got that money.
This.
Look at that. Look at those little,
What else is this?
all those little. You know what we like to say? Oh, look at that. He's got all these little crutches. He's got all
That's
the
the way I
crutches.
am.
Got all these crutches in the code.
Sure.
We got one here too in San Antonio, Paul. It's called
Look,
Power.
they're NFPA tabs.
Yeah.
Remember?
Yeah.
NFPA tabs.
Yep. What was that? San Antonio? What was that?
So we got a crutch too here in San Antonio. It's called Power, AC powered. That's how I was able to view you because we've been without power for a few days.
I'll say you got a crutch, no power. I'm
Yeah.
actually doing a video, believe it or not. I was on my board. My wife suggested that I do a video called Don't Be Texas. And it was a video that I'm going to show people how to actually have their own, put their own generator in with the interlock kit, which again, ultimately I'm going to say DIYers don't do it yourself, but I'm going to give the steps on how I would install. And at the end, it's going to say, contact your local electrician and let them come do it. But I'm going to put something together because again, a lot of people's pipes froze and all that. If they had a portable generator, that wouldn't have happened. They could have had a little heater going and would have kept the inside from getting to a certain temperature and pipes wouldn't have burst inside of houses. There's little steps that you could do. But, you know, again, our Texas grid wasn't supposed to go down because we've added so much more of that reliable wind generation. You know, that solar power is so much more reliable than fossil fuel.
Yeah. Yeah.
Yeah.
Uh-huh.
All that power is going to Colorado.
Yeah, good luck with that.
That's
Yeah.
going up to
It's warming
Jay.
warming up Jay's basement down there in Colorado.
That's
Follow
right.
the line. It goes right straight to Colorado.
You know, you got all those dispensaries that have to keep going. All right, everybody, appreciate all of y'all. Till next time, stay safe. God bless.
Peace out.
Good night.
Thanks.
Thank you.